All right, yeah, we are now on the air, live. Are you ready? You've been training for this your entire life. Hi, my name is James Mickens. I'm the host of everybody's favorite game show, Who Wants to Be a Personal Assistant to an Eccentric Billionaire? That's right, it's the only TV show that gives you, the American public, the opportunity to help an awkward rich person continue to be awkward and rich. That's John Bustamante III, worth over $97 billion. He hasn't purchased his own shoes since the late 1970s. Let's try to keep it that way and get this guy a personal assistant. Here's today's contestant. Her name is Jean Yang. She's from someplace in Middle America. I'm sure it's lovely there. Some fun facts about Jean. She is 7 feet 6 inches tall. She wrote all of the lyrics for Beyonce's I Am Sasha Fierce album. Also, Jean Yang has a capybara named Xander. A capybara, it's like a small land manatee from South America.
Basically, none of that is true. I'm a computer science professor from Carnegie Mellon University who focuses on programming languages. In particular, I study programming models that make it harder for programmers to leak secret data.
Yep, that's pretty much what I said. So let's start the interview. And by the way, I apologize that we're conducting this interview over a satellite phone made of 1980 cell phone connections. Even eccentric billionaires have a hard time with video conferencing. Anywho, what kind of experiences do you have with eccentric billionaires? Have you ever watched someone burn a pile of money and then had that person ask you to take them to McDonald's to buy them 18 large fries and a small milkshake? Then they just dump that milkshake on the ground because they're rich? Have you ever done that?
No, I generally don't go to McDonald's, but I do think that I'd be a great assistant for an eccentric billionaire. Eccentric billionaires have a lot of secrets, and I am very good at keeping secrets from leaking. For example, take John Bustamante III.
John Bustamante III has no secrets.
Did you know that he's a furry?
Are you a Jedi? Where did you get that picture? Security, there's a Jedi in here. Code red, send everyone.
I'm not a Jedi. I found that picture on his Twitter account.
That's impossible because Bustamante doesn't use his real name on his Twitter account.
But I was able to discover Bustamante's account because of information leaks. Here's what I did. I found a tweet about John Bustamante's son, Trevor Fitzgerald Montgomery Bustamante. The tweet about John's son had a link to an Instagram post. In the Instagram post, there was a mention of the son's Instagram account. Now, the rumors are true. Trevor Fitzgerald Montgomery Bustamante is no fool. Trevor knows that his dad is a famous guy, so Trevor made the Instagram account private. However, there are information leaks from private accounts on Instagram. In particular, when I tried to follow Trevor's account, the follow request was denied. But Instagram helpfully gave a list of recommendations for other people I should follow. This list included a bunch of people from the Bustamante family who all use their real names on both Instagram and Twitter. The list of recommended people also included a certain Samwise Bigfoot. As it turns out, Samwise Bigfoot only followed Bustamante family members on Instagram. As it turns out, Samwise Bigfoot's Twitter profile was only a few months old. As it turns out, John Bustamante, patriarch of the Bustamante clan, had recently made a public statement which said that he only recently got on Twitter and he only follows his family members on Instagram. And thus, John Bustamante's Twitter handle was revealed. Let me also say that this kind of unmasking was exactly what happened to FBI Director James Comey. A journalist named Ashley Feinberg was able to unearth Comey's private Twitter handle using the exact same process I had just described.
Newsflash, eccentric billionaire John Bustamante is James Comey. I can't believe it. I've been working with John for 7 years. You think that you know someone, but they hide things from you. I just want to be loved for who I am. Do you see what I'm saying?
No.
Just a little? Do you kind of maybe see what I'm saying?
No.
Okay, this is a very awkward episode of Who Wants to Be a Personal Assistant to an Eccentric Billionaire. Anyways, let's move forward. You were describing how information about John Bustamante could leak via social media platforms like Instagram. But as the old saying goes, leak my furry photos once, shame on me. Leak my furry photos twice, shame on you.
That's not actually a saying.
This article on InfoWars begs to differ. Regardless, why can't Instagram just get rid of those information leaks? I mean, Instagram hires a bunch of smart people. Why can't the programmers just fix the problem?
Well, the problem isn't figuring out how to fix the problem. Applications like Instagram generally do a fine job of protecting information that belongs to individual profiles. Things get messy, however, when applications have interfaces that span multiple profiles. For example, what happens when the application wants to suggest new friends for you to follow or new bands for you to listen to based on what your friends are listening to? What happens when an application like Instagram wants to let you search the entire universe of profiles for people who live in a certain city or have a certain interest? It's very difficult to prevent information leaks across all these recommendation algorithms and search interfaces.
Right, because of the Higgs boson. It's like being in a snowstorm where the snowflakes give you mass.
Right. Maybe what you meant to say is that it's difficult to prevent information leaks because of all the cut points where programmers have to write security checks. For example, think about a large-scale web service that contains a bunch of databases and web servers and has a bunch of complicated application logic that runs on a bunch of different machines. To prevent an information leak, you can't just look at what information is leaving the database. You also need to look at where the information is going and whether it interacts with secrets before it gets there. For example, consider our poor friend, Mr. Bustamante. Both his profile photo and username are actually public information, but the leak happened because this was shown based on private information, specifically who Trevor Bustamante was following. Figuring out where to check and what check to put depends on reasoning across the entire program.
Okay. You've convinced me that information leaks are a big problem. But guess what? I read the technology section of a little paper called the New York Times. I've read about this thing called encryption.
Do you mean encryption?
I mean, you know what? So I could check to see if you knew how it was pronounced. But anyway, using this encryption, we can just scramble all of Bustamante's data before we upload it to the cloud. And in this way, nobody can tell what Bustamante may or may not be doing. I mean, he's not doing what you think that he's doing, but so just there's nothing to see here. It's the power of encryption.
You're right that encryption is helpful in some cases. In particular, encryption is good for providing coarse-grained, context-insensitive secrecy. For example, think about the Sony data breach or the Target data breach. In both cases, the companies were storing sensitive user data in clear text form. So when attackers broke into the servers, they immediately got access to raw user information. If Sony or Target had encrypted the data, then the encrypted data would have been useless to the attacker. However, encryption has some big gaps. First of all, standard encryption schemes like RSA and AES do a poor job of expressing the conditions under which clear text data should be revealed. In traditional encryption schemes, if you have the right key, you always get access to the data. But what if a Facebook user only wants to expose your location data to the daily list of allowed stalker friends and only at certain times of day? Encryption doesn't help with managing this. This is connected to the problem that key management is hard for users too. Users have to keep track of all their keys. How are they going to do that? The reason about cryptography is probably a bad idea. I mean, people can't even pick good passwords. Let me guess. Your password is football.
Nope, not even close.
Is it Jesus football?
That may arguably be closer or warmer, but I have no specific comment about that.
That's my point. If people can't pick good passwords, it's hard to believe that they can successfully manage a bunch of keys to encrypt all their online data.
Okay, fine. I understand why encryption can't stop 100% of information leaks. But what about differential privacy? According to a Wikipedia article whose accuracy is disputed, differential privacy is equivalent in power to a 50 gigahertz RSA key.
Yeah, that's pretty big. Not quite. Differential privacy restricts how much information you can learn about a specific piece of data in the system, but not quite equivalent. Think about Spotify, the music streaming service. Spotify probably keeps track of a database of which users are listening to which songs, and that's how they let us see results of general queries like how many people have listened to Justin Bieber this week. So now let's say you and I are the only users of Spotify, then if that's the case, I see one user has been listening to Justin Bieber, and I can figure out that it's you. You've been listening to Justin Bieber this week. If there are a lot of users, this kind of query won't reveal whether you in particular have listened to Justin Bieber, because then you're just one of millions. Differential privacy uses math to quantify when these kinds of aggregate queries are allowed to prevent leaks of sensitive information.
Just to be clear, public service announcement, James Mickens has not been listening to Justin Bieber, but have you seen his recent concert poster? Dreamy.
Don't worry, James. Your secret is safe with me, and I'm sure everybody else watching right now. But the important thing about differential privacy is that differential privacy doesn't work for many kinds of services. It's designed for queries with an explicit and quantifiable trade-off between accuracy and privacy. You can make something more private by making it less accurate. For instance, saying that 18.6 million users listen to Justin isn't so different from saying 18.7. It doesn't, however, make sense to build a partially accurate social networking app in which you comment on your friend's post and then some inaccurate version of the comment is shown to the users, or the comment is probabilistically shown or not. How followed users should show up to a recommendation algorithm has the same problem.
Okay, so what I'm hearing is that there's no way to build applications which prevent data leaks. Do you want to be the one who tells that to Mr. Bustamante? I don't know if you've ever delivered bad news to an eccentric billionaire, but they tend to throw things.
That's true. Well, I mean, I personally can help Mr. Bustamante. That's why I'm on the show. I can help him by preventing data leaks because I know all the ways data can leak and I can stop it. But there's hope for everybody else too. In my research, I've been working on a programming model that's explicitly aware of information flow and makes the machine responsible for protecting secret data.
Why should I have to learn a special programming language? I'm already fluent in HTML.
HTML is not a programming language, so you might not want to put it on your resume.
Yeah, open bold tag, string, I don't care what you say, HTML is a programming language, close bold tag, booyah, you've just been HTML'd.
Awesome. I look forward to the day when I too can successfully complete the first 20 seconds of a Khan Academy video. Anyway, the reason we need a new programming model is that regular programming languages don't provide a way for developers to reason about data flows or user privacy.
Hashtag false. Isn't there a lot of work on programming languages that explicitly support information flow control?
Hashtag true. You're correct that there's been a lot of prior work on information flow control, or IFC. This work allows programmers to explicitly tag values with whether a given viewer, called a principal, is allowed to see them. Code acts on behalf of principals. A program can act on Alice's behalf, and then it can't read a value that may only be read by Bob. You can detect these information leaks at compile time before the program runs, or at runtime by tracking labeled values through the program. In both cases, the programmer has to write the program more or less correctly because these information flow control techniques can only stop the program.
That sounds great. So what it sounds like has happened is that the problem of information leaks has already been solved. So it's time to go home, folks. Strong work. High fives, everyone. Not you, Stephen. Everyone knows that you have mono. So please just seal yourself in a human-sized fish tank.
Stephen doesn't have mono. He's just quiet.
Why don't you go shake his hand then?
I don't shake hands with quiet people. Anyway, there's a problem with traditional IFC approaches. They ignore the importance of context. For example, IFC systems are good for expressing policies like only expose Mr. Bustamante's location to a restricted set of people, and then they'll stop the program before it leaks Mr. Bustamante's location to everyone. But consider what if we wanted to express a policy like expose a fuzzy version of Mr. Bustamante's location to his coworkers, but expose the precise version to his doctor. In this case, the identity of the viewer should define how the application exposes the data and not just whether the application exposes the data. There's another problem with traditional IFC approaches. I call this problem leaky enforcement. Leaky enforcement happens when a program fails to correctly handle dependencies between policies on sensitive values. For example, suppose that we want to build an online service that allows an organization to run an award ceremony. We want the service to enforce two properties. First, only people who have won awards should be able to see the list of awardees. Otherwise, people might get jealous or something. Second, the list of awardees should be kept secret until the list is finalized to allow the awards committee to play around with potential awardees before they make some final decisions. So how do we determine whether a person should be able to see the list of awardees? We have to make two checks: whether the person is in the awardee list and whether the list has been finalized. Programmers have to explicitly remember to perform both checks when showing the list of awardees. Otherwise, horrible tragedies could ensue. For example, let's say the second check, whether the list has been finalized, is missing. Then someone who was in a non-final list might look at the list of awardees, see his or her name, and then show up at the award show, even though their name is not in the finalized list of awards. Leaky enforcement can happen whenever programmers are required to manually implement a bunch of interweaving policies that depend on each other, as happens when you have to encode all your policies in terms of labels. I've talked with people in industry, and they've all said this is definitely a problem in practice as well.
I've got a bunch of industry friends too. They give me frisbees and mouse pads and tell me that my internship application was strong, but there were a lot of qualified applicants, so I should maybe try again next year.
We have to fight the darkness. As it turns out, we can dramatically reduce the cognitive burden of developers who need to prevent information leaks. We can do this by using programming models that separate out the definition of information flow policies from the definition of the rest of program control flow. For example, let's go back to the example of Mr. Bustamante's location. In a traditional programming language, we might define the following function to release his location. As you can see, it's pretty easy for the developer to forget to fuzz the data or check for a particular type of viewer. In the new model that I propose, policies are defined as standalone values, and a developer focuses on writing the correct functionality, while the programming language, the runtime, and the compiler becomes responsible for enforcing the policies. So the developer can write what's called policy-agnostic code that looks like this. The very exciting thing is that there's no policy enforcement at all. The developer does not need to specify different versions called facets or a sensitive data value. They can just define a value like this. And then the language runtime and also the compiler can determine which facet of the data to reveal at a particular sync. And now the programmer can use this location in all sorts of computations, for instance, showing Mr. Bustamante's Facebook profile, graph search over who are all the people being treated for halitosis right now, who are all the people in New York right now, how many people are patients at this medical center, etc. And all the programmer needs to do is define these values, define the policies, and then make sure that effectful computations are saying the right viewer who's seeing the values. Now, the language runtime and compiler are responsible for determining which facet of user location should be exposed in different viewer contexts. And we've also built a web framework on top of this where the framework keeps track of the viewer and the programmer just needs to attach policies directly to data schemas.
But how exactly does the programming model determine which facet to expose? I mean, what foul stratagem or witchcraft have you brought into this fair land? I cast you out, demon. I cast you out.
As it turns out, witchcraft isn't necessary to determine which facet to expose. At a high level, you just have to fork a new copy of the program whenever the execution path manipulates a faceted variable. You create a new copy for each faceted result. For instance, if I want to know how many people are being treated in this halitosis medical center, there's one copy of the program for the actual location and one copy of the program for the city. Later, when the program executes a viewer-dependent operation, the runtime determines which universe contains the appropriate facet to reveal and reviews that one.
Awesome. So running an exponential number of program copies sounds super efficient. So is the name of your programming model massive computational overhead? Or maybe it's called, I don't know, a 96 core machine struggles to run a faceted version of Hello World?
Well, James, we have to think outside of the box here.
But I like the box. The box smells like cinnamon.
While you were inside the box, trying to become one with the spice, my research group discovered something interesting about faceted programs. It's true that a large number of program copies are necessary to formally describe the correctness properties of faceted execution. However, from a practical perspective, multi-execution, this simultaneous simulation of different program paths, is frequently unnecessary to actually run a faceted program. The reason is that if we know where the value is going to go, we can just throw away all the other facets. And often, for instance, for the web framework, we know where that value is going to go. It's to the session user. And it turns out that we can also achieve an approximation of the multi-execution semantic by rewriting the program at compile time. We've been working on a static approach that will figure out where to insert conditional permissions checks into your program before it runs, so we know whether the program is allowed to use a sensitive value for the given viewer or it should use the default alternative value instead. Programmers express these checks as fancy types called refinement types. Refinement types are fancy because they can depend on program values. For instance, you can say that an integer x is allowed to exist if it's greater than 0, or if the viewer is Alice. The compiler then has to prove this property in order for the program to run. Our system uses type error localization to figure out where checks need to go, and then synthesizes the appropriate check from the type. Quite magical, if you ask me.
So witchcraft is involved, just as I suspected. Look, Mr. Bustamante is a temperate man who normally does not tolerate the supernatural, the arcane, the eldritch, or the Lovecraftian. Now, he might make an exception in this case, but how do your fancy types stop leaky enforcement?
Well, the nice thing about these policy-agnostic systems is that they manage all the policy relationships for you with respect to the program. And we have a guarantee of non-interference and also policy compliance according to a detailed formal semantics that we've expressed. And so to explain what our security guarantee is, let's return to the example of a program that manages award ceremonies. We enforce a version of standard non-interference that takes into account this additional fact that policies might themselves depend on sensitive values. The standard non-interference guarantee in information flow is that if a viewer isn't allowed to see a secret value, then the secret value could be anything, and that shouldn't affect the output. In our case, secret values can influence whether a viewer is allowed to see secret values. For instance, consider the policy that you have to be an awardee to see the secret list of awardees. So we have to think of this space of secret awardees in two parts. Viewing of the secret value, if the viewer is in the list of awardees, and those that don't, if the viewer is not in the list. The space of those that don't should be indistinguishable. If you aren't allowed to see the secret awardee list, then the list can contain Bustamante or Comey or Justin Bieber, but you shouldn't be able to tell.
Okay, this all sounds fine, but we know that programmers are lazy. They don't want to write test cases. They don't want to write comments in their code. So I'm guessing that a lot of programmers will not want to write policies. So what happens then? We can't just go to the policy tree and wait for a policy acorn to fall to the ground and then try to shove that acorn in our program. It's been known for years that acorns do not belong in computers.
Policies do need to come from somewhere. Fortunately, some of my current research is about exploring how we can retrofit existing programs to a policy-agnostic model. For example, I'm looking at automated techniques for extracting policies from regular programs and for propagating these policies. Once the policies have been extracted, we can then add enforcement using a combination of the static and dynamic approaches that I've been talking about.
Well said. And on that note, let's conclude this very special episode of Who Wants to Be a Personal Assistant to an Eccentric Billionaire? Today, we've experienced the gamut of human emotions. We've laughed, we've cried, we've learned about the tragic intersection of dandruff, halitosis, and refinement types. And oh my goodness, we've got a very special someone approaching the set. It's none other than Mr. John Bustamante himself. Come on down. Mr. Bustamante, what do you think about policy-agnostic programming models? Yeah, Sometimes I pour the tea with the crumpet at £2, 6 pence. The tardigrade can survive in space. Paddington, Time Lord.
You weren't kidding about the eccentric part.
Acorns inside the computers to make them safer. So true, Mr. Bustamante. So true.
Wow.
My hand looks like a spider. Monsters aren't real, Gene. What do you?
I'm gonna do that part over. Well, you're in
nice box. It's like YOLO. It's like the most awkward form of mansplaining. Christmas time is here. La, 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 la. I basically have perfect pitch.
I don't believe in objects.